second day of our school on quantum probability. There are some very important information that we have to pass. One of the information is that we all have to be seated by 9. The program was, these are the general. We have teachers that will be teaching us from online, and they have time which we have scheduled for them. So whatever it takes, I mean, we cannot afford to make any shift in time because their programs are run that way. You must understand that. If there's anything to be adjusted, that will be based on, I mean, other things, but not the timing of the school. And please, we want this to hold from today. You see, this is the time we are commencing the program. We must commence at that time. So I think 10 minutes break, 10 minutes break. Okay, thank you very much. So Professor Kadi is going to give the first talk, and Professor Olu will give the second.
And once we have the scalar product, which means the state on the algebra of polynomials, we can define the orthogonal projection. Because we have the pre-scalar product, and we can define. There is a lemma that I have not proved here, but it is the proof is in the notes that also for pre-Hilbert space you can define orthogonal projections in a unique way. So the orthogonal projection from the all polynomials to the polynomials of degree less or equal than n is well defined. So if I have a monomial, I can subtract its component on the space of polynomial of degree less or equal than n. And this gives a new polynomial which have a very special property that the highest degree term, which is x to the power n, has coefficient 1. Such kind of polynomials are called monic. So a monic polynomial is a polynomial whose highest degree term has coefficient 1. You see, this polynomial, why this is the highest coefficient? Because by definition, I am projecting on the subspace of polynomials of degree less or equal than n minus 1. So the result of this, I start with a monomial of degree n, but I obtain a polynomial of degree n minus 1. Okay? So that is why this is the highest coefficient. So, once we have the sequence Pn, the sequence Pn is called the sequence of orthogonal polynomials associated to the probability measure mu, and we know that to give a probability measure is the same thing as to give a random variable. So either we say associated to the probability measure mu, or we say associated to the random variable whose distribution is mu. So this is a orthogonal, this is called the orthogonal, the gradation, the monic orthogonal gradation, because the Phi n are the monic polynomial. Then we did not give the proof. I will give the proof because this is really a fundamental theorem, and as you will see, the proof is not so difficult. But now we will go on a quick ride on the main ideas. So we will not stop on technical details of tools. When I have finished our ride of the main ideas, then we come back and we give some proofs. The most important one, not all. Okay? So this is the fundamental relation. What does it say? It says that if I multiply the nth orthogonal polynomial by x, then I obtain a new polynomial which is orthogonal to all other polynomials with the exception of only 3 indices. -1, n minus 1, n, and n plus 1. This you have to keep in mind because it's the fundamental relation for the whole theory. from this relation, it follows in a simple way that we will see, and we will see the proof in a future lecture. From this relation, it follows that if I multiply x times xn, I have a polynomial of this form. Look, the phi n harmonic. So phi n plus 1 is also monic. And so if I multiply a polynomial, a monic polynomial phi n by x, I still have a monic polynomial. So this justifies why the phi n plus 1 has no coefficient. But phi n has a coefficient called alpha n, and phi n minus 1 has a coefficient called omega n. Now, this omega n as alpha n are identified in this way. Omega n is defined as a lower diagonal term, matrix coefficient of x, in the basis phi n. And alpha n is the diagonal term in the same basis. So the scalar product of x phi n times phi n. Okay. It's obvious that the alpha n is real. This is true whatever the vector phi x, because x is Hermitian. Why this is a real number, omega n? It is a real number because the monic orthogonal polynomials have all real coefficients. So x, of course, is a Hermitian, so real value, random variable, and therefore this scalar product is a real number. What is less evident is that it's positive, but this is a theorem that we will prove. Now I will introduce the last property that we introduce is this. We introduce the notation omega n factorial is a generalization of the standard factorial that you study in university or some, or you in the school. Here it means simply the product from 1 to n plus, well, this is not n plus, that's a correction. Okay, it's the product from 1 to n of the secret omega j. But if we add the analog of the standard convention in probably in analysis, that the 0 factorial is 1, which will say omega 0 factorial is 1. And then we can begin the product from 0, not from 1. With this convention, the norm of phi n is omega n. Okay? This is a very famous result of the theory, analytical result of the theory of orthogonal polynomial, but we will give a purely algebraic proof of this famous result. Now it comes the crucial point of all my lectures and all our course, which is the quantum decomposition. So, and the quantum decomposition, we will see, is a different way to interpret a certain relation which was known 150 years ago. This relation is called the three-diagonal monic Jacobi relation. It means, and I have rewritten what it was already written here. We already wrote in the theorem this three-diagonal, this relation. This relation has a famous name, is called three-diagonal Jacobi, monic Jacobi relation, and it is the basis of our course. I want to warn, if there are some people from physics who are present here, that in physics they don't use the monic Jacobi relation, they use the so-called normalized Jacobi relation. And so there is a coefficient also in n+1, because they use not the monic polynomial, but the normalized polynomial. Normalized means that you replace Vn by fitting the n, which is Vn divided by epsilon. Okay? Now look at this relation. We naturally suggest this relation, the right-hand side of this relation, the number 304, naturally suggests to introduce three operators. So the first operator is, see, on the left-hand side I have x acting on Vn. On the right-hand side I have Vn plus 1. But I can define an operator A dagger with the property that A dagger Vn is equal to Vn plus 1. Similarly, here I have alpha n Vn. So I can define another operator, alpha A0, with the property that A0 Vn equal alpha n Vn. And here we have omega n Vn minus 1. And so I can define a new operator, A minus, with the property that omega n minus Vn is omega n Vn minus 1. This operator, which increases the gradation, will be called creator. This decreases by 1 will be called annihilator. And this keeps the gradation in itself. So it preserves the gradation and we call preservative. But with this notation, now this vector, this is a vector and an identity between vectors. But if we introduce the operators and we can write this relation, the Jacobi relation 304, we can write as an operator relation for every n. This is still a vector relation, but this is true for any vector. Now we have some operators which are everywhere defined on the pre-Hilbert space, and this is a basis of the pre-Hilbert space. It means any element of the pre-Hilbert space is a finite linear combination of Vn. So to say that these vectors are equal for all n is exactly the same as saying that the two operators are equal. That the operator multiplication by x is equal to the operator, the sum of three operators. And this is the fundamental new idea of probabilistic quantization. Okay? So this formula you have to keep in mind that x is the sum of three objects. You see? And that is why this formula is so important that we give a name to it. We call it the canonical quantum decomposition. The term canonical is not to emphasize rhetorically, but simply because any random variable has many quantum decompositions. I can invent uncountably many, but there is only one which is canonical and which is this one. Okay? This is a topic I will not go very deep, but it is so. So the three operators we already said, they are called creation, annihilation, and preservation, and we abbreviate the name and we call the CAP operators, because creation, annihilation, and preservation. Okay? So the meaning is very important, you see. As you see, this is mathematically is almost trivial, because we did not prove anything. We simply changed the interpretation from a vector identity to operator identity. But this change of interpretation has very deep implications. And my course will be dedicated to explain to you these deep implications. Okay? Now, let me go back to the main. This is the summary of the previous lecture. Let me go back to the new material. Remember, we have not given any proof. Now, in the quantum decomposition, there is one very important point, that these operators, A plus, A0, and A minus, have some very special properties. The fundamental point is this: A0 is a Hermitian operator, so is equal to its adjoint. And A dagger adjoint, the adjoint of A dagger is A minus. And you see, in physics, you will not find the notation A minus, because in physics they use simply the notation, and we will also very often use the same notation used by the physicists. But so I write equivalent. In the physics literature, you don't find E minus, you find A, but when we do calculations, it's convenient to have A plus A minus. For some complex calculations it helps. Then, okay, as I said, I will jump the proof, but please, in the note, there are exercises. Try to do these exercises, because in the tutorial, you have distributed the notes. You have received the notes, everybody has received. So, okay. So try to do, because this will help you. Yeah. This will help you to understand if you have a deeper feeling, a grip on what we are saying. And if you have difficulties, you can ask me, and in the tutorial we can discuss them. Now,
I want you to try to, with this direct formulation, compared to what we have always used in the quantum field theory case, like the ultimate case, our annihilation relation and range, that is.
We will arrive to this, but I hope to arrive to this relation in this lecture. Don't forget that we are doing only the one-dimensional case. In the case of stochastic calculus, then we have a random process. However, it is a very simple random process because it's a product type. So everything in this kind of processes, everything is reduced to one dimension. That is why I lose so much time in one dimension. Because in the standard physics, all mathematical products are reduced to one dimension. Because the star lecture is only considered product. We are beginning to consider real interaction, non-product. In the Hansen-Patterson case, we are still in the product field. So everything is reduced to one dimension. So that is why you have to have a solid understanding of one dimension. Because then infinite dimension will be out, the factorizable infinite dimension, is equivalent to product, will be very easy for you. And then there is a jump in the difficulty when we do non-factorizable. And this is the new research horizon, which some of you might be interested in. Okay? So there is one proof that I will give you because it is only one line, and it is the following. Take the action of the annihilator on the vacuum. You see, then consider any n and consider the scalar product. But by definition of adjoint, you remember the fundamental property I said is that the annihilator is the adjoint of the creator. Okay? So when I am yes, this is what it. When I have the scalar product, I can bring on the left side and I find the adjoint. But what is the adjoint? Remember, the creator, the monic creator, so it adds 1. So whatever is n, even if n is 0, here I have 1 and here 0. But the phi n are an orthogonal basis. And so this scalar product is always 0. Okay? Because the phi n are orthogonal. Okay? And so this can never be 0, n plus 1, whatever n is, because n starts from 0. And so phi n starts from phi 1. So what does it mean, this? This means a property that is very important in physics, that I wrote somewhere, but here you don't find. Let me see. I didn't try, but I will write here. Where?
Animator, it's orthogonal to all the
exactly.
It's there. You have
So
passed it. It's there. Yes. Just after the proof that you showed that.
Sorry, I'm just more than
yes.
So and then I forget to write that this is equivalent to say
yes. So the animator returns orthogonal to
this is equivalent to say
space.
Spelling of property.
exactly. I'm showing that this is very famous in physics. So I want to show how this comes from the probabilistic approach as a deduction, not as a definition. Okay, we deduce that the property. This is what you were saying. Right. Thank you. So, you see, this is a very famous problem. The annihilator kills the vacuum. That is why it's called annihilator. Kills the vacuum vector. And this, in our probabilistic approach, is a theorem. In physics, is a definition.
Is there any difference between the creator and the right shift, and then annihilator and the left shift operators?
Yeah, in the monic basis, the creator is identical to the right shift.
The right shift.
Right. But the annihilator, remember, the scalar product is not just the L2 scalar product. It's L2 of mu. And this omega n keeps the track of mu. You see? So the left shift is not simply the annihilator is not simply, but it's the weighted.
Yeah, it's weighted.
The weighted left shift.
Great.
And the weight keeps the memory of mu.
Yes. Okay.
It's very important. So let me come again to this point, because the quantum decomposition is really the fundamental new idea of all these things. Okay? The quantum decomposition conceptually means that any random variable, which is classical, and random variable commute because they are multiplication operators, but they have a non-commutative microscopic structure. And today we want to study why, and not only non-commutative is simply negative, like nonlinear means nothing. Negative definition are very vague. But here we will see that non-commutative is very, very, very special. We have a very special multiplication. And now we are going to see it. So before this, let me introduce a conceptual implication of this fact. You see, we started that, remember the definition of algebraic probability space, I remember it in the summary. It's just a pair where you have a star algebra and a state on the star algebra. A state means positive, normalized linear function. Okay. Then this is called classical algebraic probability space if A is commutative, and quantum if A is non-commutative. Now we started from a classical algebraic probability space, which is the algebra of polynomials with the state given by the distribution of x. Now, but we know from the quantum decomposition that x is the sum of three objects. So what we can do is to say, let us ampliate the algebra of polynomials. So the algebra of polynomials is a fundamental object of mathematics. But now, when this polynomial corresponds to a probability measure, we ampliate this algebra. And since using the fact that x is the sum of three operators, we consider the algebra whose generators are exactly not x, but the cap operator of x. Creation, annihilation, and preservation. You see? When we have the cap operators, we have a new algebra. This algebra, moreover, this algebra is an algebra of what? It's not an abstract algebra, because A dagger, and A0 are operators on the pre-Hilbert space that is the P phi 0. You remember the pre-Hilbert space of all polynomials with the state with scalar. So on this algebra, and you remember that the vector on this algebra, we have a natural state. Which is this state? Is the state, because you see, these are every element of this algebra, the quantum algebra, associated of the random variable x. Any element of this algebra is an operator on the pre-Hilbert space. So define, don't forget, we are in pre-Hilbert space because we have the great advantage to avoid domains. These are, I told you, these usually are unbounded. And when you have unbounded operator, you have a lot of problems with the domains, their domains. However, since we are working in the pre-Hilbert space without completion, all our operators are everywhere. We have no problem with the domain. They act on the polynomials and they make polynomials into polynomials. So they are a very, very special type of unbounded operator. And we algebraically exploit this very special. So we all this discussion was aimed to explain why I can always speak of Z applied to phi 0. Z is usually unbounded, but phi 0 is always in the domain because every vector in the Hilbert space is in the domain. Okay? So I have a quantum extension of the classical integral that we wrote on this bracket phi 0 expectation value in phi 0 expectation value is the quantum extension of the integral with respect to the probability, but now it's defined on a much larger algebra. You see? And so it gives you a state. It's obvious. Why a state? You can prove that this is always positive technique. In fact, we gave the proof yesterday in the tutorial in the connection with the momentum problem that this map as a function of z is a positive definite function, and we gave the proof of this. And then, therefore, we have a quantum probability. So let us sum up. We started from a classical probability space, P, a commutative algebra state on it, and we go to another quantum probability space. Why we say that this is an extension? What do we have to prove? Can you imagine? There is something that I did not yet say, but there is something to be proved, to speak, to say that this quantum probability space is an extension of this classical probability space. What has to be proved? Well, we have to prove first that the commutative algebra of polynomial is contained in the quantum algebra.
Yeah.
Okay? And then what else we have to prove? Remember, algebraic probability space is two objects. An algebra, a star algebra, and a state. Now we have this, the star algebra. We have to prove that P is contained in the quantum version of the quantum algebra. What else shall we prove? We have to prove what? That the restriction of the quantum abbreviation to the classical algebra is the classical expectation value that you have. Like, okay? But this is completely trivial. Why? Because this is completely trivial. Because if you remember, what does it mean, the square norm? The square norm, in fact, I will now use the notation that we are using for the. It's good to have also some alcohol so that we can easily now we need. It's better to use this notation that we are using everywhere in the notes. So this polynomial multiplied by, but what is phi 0? So this is the scalar product. Is this, okay? Now, you see, this means that I can write this scalar product as because this if Q belongs to the real algebra, polynomial algebra with real coefficients, not complex coefficients. If I take a polynomial with real coefficients, the multiplication by this polynomial will be a Hermitian operator. So this scalar product will become like this. And since Q has real coefficients, it is Hermitian. So this is simply You see, this is the proof that if I take the quantum extension and I restrict to this usual polynomial algebra, I get the standard. So also the restriction of the state, of the quantum state, to the classical algebra gives the classical expectation. So we have an interesting result, because we have shown that the quantum algebra, which is the algebra, why, yeah, I don't, but the proof is very easy. Why the quantum algebra, that is the algebra generated by A plus, A0, A minus, and well, the identity is not necessary, but I show. This algebra contains strictly the classical polynomial algebra. Why? This is because this is the algebra generated by X. So, but X, what is X? Is A dagger plus A0 plus A minus. So, every polynomial in X is this. It's a polynomial in the non-commuting variables. So, it is in this algebra. And this proves this. Okay? So the quantum decomposition is the essential point, that we have really an extension of the algebra. Okay? Okay, I have 10 minutes and I would like to tell you in these 10 minutes, without proof, and jump all the comments. So, this is an easy but important notation. You see, if I have any Hilbert space and I have a gradation means that this pre-Hilbert space, let us say, or it can be any vector space. Here we don't need scalar. So, if it is a direct sum of subspaces, I can always define what in physics is called the number operator. This number operator in physics plays a very fundamental role. It's essentially is the generator of the so-called free dynamics. So it's very important. And how you define? Very simple. If you have an element of the n space of the gradation, this operator is identically equal to n on the subspace of the nth gradation. So if I can define a function of this operator lambda by if f is any function from the real number, from the natural integers to the complex values, I can always define a new function by saying that the phi n are eigenvectors of phi lambda with eigenvalue and n. So they are completely defined on the pre-Hilbert space, because any element of the pre-Hilbert space is a finite linear combination. This is extended by linear because the phi are orthogonal. So with this notation, let me consider the orthogonal polynomial gradation. So I can define the number operator in the orthogonal polynomial gradation. And I can define any function of the number operator by this. Remember, this means that phi n, nth orthogonal polynomial, is eigenvector of f lambda with eigenvalue of n. Once we have this, we have the first example of multiplication theorem. Remember, A plus is the creator, A minus is annihilator, A0 is the preservator. And if we take a function of lambda, we are generalizing the preservator. Because by definition of preservator preserves the gradation, and so is a function of the lambda, the number of graphs. So what we have is, this is really very important. First, non-trivial result. It's very easy to prove. We will see the proof, but enormously important. So if I want to multiply two kappa operator, when I write A epsilon, I mean that epsilon can be plus, minus, or 0. But here I have epsilon left, and here I have epsilon right. So this can be arbitrary. I am multiplying two arbitrary kappa operators. And what I have? Either I have the square, if epsilon r, the index is the same. If I multiply, if this is plus and this is plus, this is obvious. I have a plus square. Of course, if minus the same. If this is minus and this is minus, I have a minus square. That's the same for C. What is really important and very special of the new approach is that if they are different, and what does it mean that they are well, that you see here I am restricted, I am not allowing with 0 here. I am restricted to plus and minus. So if they are different, there are only two possibilities, that the right is plus and the left is minus, or the left is minus and the right is plus. These are the only two possibilities. I am insisting very much because in this multiplication, there is a very powerful, it is hidden, but we will make explicit. There is a powerful generalization of a very well-known technique in physics, which is called normal order. Our approach is much more than normal order. And this much more is exactly this word. And I will explain why. So I want to spend some more time in this. Just I have one minute, I will take 1 minute more of my time. Just to show you and to comment you this word. So this is the first multiplication table. And you see that this multiplication table is, what happens if I multiply a creator or an annihilator times a function of the number of vectors. You see, here function is on the right, here it goes on the left, but with a change in index. See? I show you maybe you are not familiar with the notation, but the notation is this. Remember that I have f lambda acting on the nth orthogonal polynomial is fn times the same. And fn is a number, so fn is an eigenvalue of f is a number. And it can also be complex, but in general can be complex. But if I take f lambda to be omega lambda, I have this notation: omega lambda plus k acting on f n equal f. Sorry. Is omega n plus a b. And here omega n we met in the three are those that we met in the three-diagonal Jacobi relation. So they are positive real numbers, strictly positive. This is by definition. Okay? So now this formula is very important because it gives you the first example of probabilistic commutation relation. And this formula, taking the adjoint of this, you essentially prove this. So the fundamental formula probably is this one, is easier with the plus. Taking the adjoint, you take this, you obtain this. And this is the, supposing this formula true. Well, I suggest that you prove as an exercise this formula. Using by definition of f lambda, it should be very easy for you to prove this formula. Okay? But this formula is very important because it's the first example of non-commutative. Because you see, it's non-commutative. Because here it's not f lambda, it's f lambda minus epsilon. Okay? So it is the first example of non-commutative relation which are coming out from classical probability. We never spoke of quantum physics, never spoke of quantum mechanics. We are in classical probability, so this is really an important first example. And this is the sequence. Tomorrow we will complete the discussion and we will make the bridge that Professor Ezekiel was asking for with the standard boson quantization. Okay?
So, I think this XL sub R, that's in the braces.
What?
Oh, XL sub R.
This?
Yes. The second, I think it's plus, not minus plus.
Ah, yes, it's plus. They are opposite. You are right. You are right. I will correct. I will correct immediately. It's a misprint.
That gives the number operator optic and accelerative that's A minus A plus.
There are disasters. By the way, I am very grateful if somebody of you reading the notes and finds some misprint or some obscure point. It's very helpful if you tell to me and we clarify or correct where it is necessary, like in this case. Yeah. I don't understand. So I have finished. Thank you very much for your attention.
So, let's give I don't know if you have questions. Okay, somebody online is asking questions. Okay, Professor Lee is asking.
Yes? Tell me. Yes, of course. But no, so if it is very okay, if a problem that you think that everybody can understand the formulation, then good. But if it's a problem that is for us, let us say, then it's better that we discuss privately. It's a problem that can be of interest for students. Then, very good. Very good. So let us see, what is the problem? Hello? The organizer is activated in the audio. Ah, no, yes. So, that I can, no, wait a moment. Is it? First, they gave me the chance to activate, but now it doesn't give. I don't understand. Okay, now but I don't know if you see the screen. You see this?
I think he wrote some chat on the chat box. He wrote some expressions there. Maybe you copy and run it. Is that it?
No, let me see.
Yeah, the self-adjoint of operator X implies that let us have formula.
Just a moment. Let me see if I can understand. Chat. Here.
Yes.
Ah, there are 12.
Yes.
12. Oh my God. I can't hear. It's no problem.
Go down to the chat.
Yes, because they were protesting.
Yeah.
This is.
Self-acceptance of your equator X.
Yeah. This is one of the things that I did not prove. I gave as granted. When I will be in the second part of my lecture, when I will give the proofs, I will explain why this apparently strange fact is happening. It's a symmetry. It's essentially the tridiagonal Jacobi relation, but it follows from. I think now is I don't want to give the proof. As I said in the beginning of my notes, I want to give the fundamental new idea. Then we go into the technical details. When I will give the proof, we will explain this. Okay? The possibility of what? I think this is a very technical problem. It's better that we discuss together. I think it's very difficult for the audience to follow this discussion. Let us discuss together after your talk. After when the session is closed, we will discuss this together. Okay? Okay, let us do so.
If there are other questions, and for those online, they can unmute themselves and ask questions. If you are online and you have questions, please unmute and ask. The last page.
The last page. Yes.
Yes.
So they people will understand.
Yes, my question is the left echelon left and right is a possibility of 4 values.
4.
Yes. So
No, 4. In fact, now only
4 combinations.
Look at the first line. The 2 epsilon r. Now I am restricted to plus and minus. So I have only either they are equal, and there are 2 possibilities, or they are different and still 2. 4
yes. So 4 combinations.
Correct.
Yes. So
Correct.
yes, I have not seen the connection with the 96.
With
4 possibilities.
4 possibilities.
The 4 possibilities.
The 4 possibilities, well, you have the symmetric one in some sense is trivial. See, because there are 4 possibilities, but you see,
because if you have +1,
Yes.
-1, -1.
Right.
If you have
you have 4 possibilities. Well, let us do explicit. It is better. Okay. So this will give you a hint. I prove this equality for 1 possibility, and I suggest you to generalize for the other 3 possibilities. Okay, let us take, for example, this relation. We want to prove this relation. So we start with lambda and a epsilon. Let us suppose that epsilon is plus. Okay? No, your question is this. Right? So let us consider this. Your question is for. So let us consider this possibility. A
+1, A +1.
Okay. A dagger. This in physics is because when you have in physics, let me anticipate. When you have all creators on the right and all annihilator on the left, physicists call this normal force. Okay? So now we want to know in physics you have the commutator. And as I explained, we have much more. We have the exact expression. Much more, because of course if you have the we will see that once we have the expression or the multiplication, we have also the commutator. But not conversely. If I have the commutator, of course I have not the expression. See? So that is why this is much more. Let us prove this equality in this case. How do we prove? Apply this to the operator. By definition of annihilator, this is equal omega n phi n minus 1. But I have still a daga. Okay? A daga will bring back to n.
Yes.
Because remember, a daga phi n is phi n plus 1. So this n minus 1 plus 1 is n. So I go back to n. But this is true for each n. And the phi n are a finite linear basis. So it means it's true on the whole Hilbert space. Pre-Hilbert. Okay? So this, what we have proved is equivalent to saying that A so this corresponds to this formula with epsilon n equals 0. Okay?
So we are supposed to show 4 of such. That is, there are 3.
And then you, as an exercise, do the same with A and anti-normal. It's simply an exercise. You see, very simple. In this case, it's very natural. But this is very powerful. And I will try to explain why. These two formulas will, no, 3 formulas, this and this, will be very powerful, which will allow us to have enormous simplification with respect to the formulas that you find in the physics literature. Enormous.
So my second question, Bob, I was thinking maybe you are going to discuss the Faber lemma since connected, right?
The Faber lemma, yes. Faber lemma is fundamental because, you see, why Faber lemma is fundamental? Because, let me anticipate this. What we have proved in this lecture. In this lecture, we have proved that if I have the classical algebraic probability space, that is a state on the polynomial algebra, yeah, I find this, I can form the orthogonal, monic orthogonal polynomial sequence, and I can prove the three-diagonal Jacobi relation. So, I can form, for the three-diagonal, I can deduce, we have seen the explicit form, alpha n, and we have omega n. So, we show that if we give the polynomial algebra and the state on it, we can form the monic orthogonal polynomials. And there exist two sequences, alpha n of real numbers, any real number, omega n of positive real numbers. Okay. This is positive. Favart lemma is the converse statement of this. See, you start from the sequence, the two sequences, alpha n, real number, and omega n, positive real number, and you so deduce p. Well, in fact, p is universal, so you deduce that there exists a state phi such that if you apply, this is the first part of the theory, such that if you, this is the second part of the theory, such that if you apply the first part of the theory to phi, you find that the two sequences from which you start. Okay. So, Jacobi start from polynomial and probability measure, which means state, phi, and deduces the existence of this sequence and of this orthogonal. Favart starts from two sequences and constructs a state on the polynomial algebra. Once he has this state, he can apply the first part of the theory. The non-trivial point that he will find, a priori you can find different alpha n. But if the Favart lemma that you can do the construction so that you find exactly this is the, but we will, is in the note and we will discuss tomorrow. I wanted to arrive to the multiplication table, or the Kepler operation, which to me seems more important. From the general theory, Favart lemma is very. It took 16 years to prove the analog of this in dimension greater than that.
So 97 and 98 gives us a generalization of left antipalasarati and right antipalasarati.
Yeah, because in factorial, but this is different because Partasarati they don't reign in this. They automatically in the Hassan Partasarati case, Pn are Hermite polynomial. They fix it, so it's not the general property. Only fixed. They only one measure Gaussian. Okay. So and in physics, only one. Again, Gaussian. But we are developed the general. Unfortunately, the analog of this pair of sequences with dimension greater or equal than 2 is more common. They are operators. But I think I will not have time to discuss this general multidimensional. It's much more difficult than the standard.
Okay, so any question? Okay, please. What? And that's a question. You were asking. So he asked.
You
mentioned.
Please speak loud.
Okay, sir. You mentioned earlier on. Yes, sir. I see you mentioned earlier on that normally in the physics aspect, they usually focus more on the one dimension, right? One-dimensional space, right?
What do you think?
I mean, you mentioned earlier on that in physics, you normally focus on the one-dimensional space, right?
I said
question.
what is the question?
Okay, question. I've not really gotten the physical application of this algebraic and analytical presentation you have been making, really, especially that aspect, that A dagger and A minus and A0, when we're talking about how it is the creation and annihilation and
Do you want to know how is the connection between the general probabilistic creation, annihilation, and the zero, and what is the physics one? And that for this we need. I wanted to do today, but I did a long summary because I prefer to go slowly, but you understand. Instead of running, and you don't understand. So I want to insist on the important things. Tomorrow we will clarify this, and you will see that it's very nice and surprising. Yes.
Prof is from physics.
Good. Very good.
Somebody also has a question. Please speak loud so I can hear you, and maybe a bit slowly.
Thank you so much, Prof, for the presentation. Equation 304. Why you were presenting equation 304? Why you were presenting
304. Let's see, what was it?
Yes. My own is everybody from the other is on security principle. So we have probability different.
If the coefficient AN becomes alpha n becomes 0, what will the entire equation become?
That is the you see,
No, it cannot be 0.
there is this is an important question.
The sequence fits from
The question is, what happens when alpha n becomes 0? Okay. Now, one of the fundamental theorems of the theory of the probabilistic quantization theory is the following, and it is in my notes, and we will meet this theorem. I hope tomorrow, because it's important to make the bridge with the Gaussian. The fundamental theorem is this theorem. The sequence alpha n is identically 0 if and only if mu is symmetric. Symmetric means that if you take the odd moments, they are all zero for any k. So you see, in physics, alpha n is always zero. So this means that the quantization that was used by physicists was neglecting all non-symmetric measures. But now we understand quantization from a higher point of view. So we include the non-symmetric. Thank you for the question. You were asking the question.
Now, in 308, equation 308, yes,
Vector, still vector.
A plus plus A0 plus, okay, A dagger plus A0 plus A minus, or plus A. Supposed to be A minus. Okay.
I have explained. You see,
Okay, yeah. Okay, they are the same.
I always use this.
Yeah,
A minus.
okay, adjoint.
In the physics literature, it's always.
Physics, they write things like that.
I use intuitive, but I agree. I am too correct. Because the notation must be coherent.
Okay.
Yes. Yes. Okay. So you were asking something or no? You were asking something? Yeah. This is a very fundamental question. You will see why. These two relations here, they will allow the two relations that we wrote before, this multiplication table, will allow, from there we deduce commutation relation. But we have much more. See? Of course, when you have the product, I already said, when you have the product, you can deduce the commutator. But it's not true that when you have the commutator, you can deduce it. So product is much more, contains much more information than commutator.
Okay. In the absence of any other question, let's give Prof a round of applause. Okay, so yeah, this is 11.
So,
and the timing is 1 hour. Yeah, so it will take 11 to 12. Yes. So Professor Lu, you can come online and.
no, wait a moment. But, so we don't do the coffee break. I
Do
think
the coffee break after.
after. Ah, good. So 11 to 12.
So let me make him co-host.
Okay.
So that I can